Okay, it looks like it's time. Welcome back, everyone. I hope you all had a good spring break. For me, it was mostly a catch-up week, and they never seem long enough. But the exciting news for us is we're in the final stretch of the semester, including this week. We have 6 more weeks to get through. It's going to feel like they go kind of fast, but we'll be doing the same kind of pace as we've been doing through the prior part of the course. Looking forward in the schedule, the next thing we have coming up is an ordinary week on week number 12. But then we have exam 3 coming up on week 13. So this is the week I'm on where I'm going to start getting prepared on doing the same exact things that we did on exam 2. On Friday, I'll start writing out what the formulas will be provided on the real exam 3, some review problems, 2 sets, just like exams 1 and 2. And really, we're just going to do the same exact rigmarole all over again for the third exam. But that's what we have going on so far. Other big announcement is, well, not really a big announcement, but I have an office hours interruption on Wednesday for a dentist appointment. Didn't seem like a good idea to combine both of those. I'm not excited about doing a dentist appointment on April Fools, but I'll get through it. We'll still have class as normal on Thursday. But any questions or comments at all, folks, to start us out? Okay, well, let's get started then. We left one example on strong induction across the spring break, which is probably a good idea. We get to refresh just what we were doing in that section. The main goal of this section 5.3 in particular wasn't just about induction, it was also about writing out pseudocode and then using induction, in particular strong induction, to prove that that code would run as intended. And we're going to continue that theme as we go to the next chapter on number theory, section 7.2. We're going to look into a modulus and a divisor algorithm, the Euclidean algorithm, and then many other types of algorithms as well in chapter 7. I think chapter 7 will be kind of an exciting one, new topics. So we'll see how this goes as a fresh start. But first, let's review how strong induction, really induction in general, goes. This is just an extension when we say strong induction by returning to the sequence, the Fibonacci sequence. This is kind of a neat sequence. This was not necessarily discovered by Fibonacci, but it was introduced by him. This is something that was first investigated, list what we have historically, way back in ancient Indian mathematics. So the idea is with the Fibonacci sequence, we start with 2 initial values. The first term in the sequence is 0. It's infinitely many terms. We express it in this way with that notation. The next term is 1, and then to produce all of the next terms thereafter, we sum a prior term and 2 prior term for all n greater than or equal to 2. So for example, if we want to find the value for f2, we go to the term f0. We have that value, it's going to be 0. Then this part right here says take the term. Well, this is for, hang on, I got these backwards. Let me try again. Been a long break. Indexing is not working as intended. So I'm doing F2, so placing the value of 2 here. This would give me an F1. Might as well just write that in and then put it in. Then placing 2 here would give me a F0. I got the F1 and an F0 backwards. Probably not a good way to start off introducing the sequence. But then when we go to substitute in the values, we have a value for F1, which is 1. F0 is 0. So it tells us the second term of the Fibonacci sequence is 1. But really the whole heart of the sequence is we add together the 2 prior terms. So likewise, if we want the third term of the Fibonacci sequence, we take the second term, which is 1, plus the first term, which is 1, to get a 2. Let's do one more just because we have a space. If we want the fourth term, we take the third term. That's what the fn minus 1 is saying. Third term has a value of 2. Add to it, this is 4, so it's going to be the second term. So that's 1 prior term, that's 2 prior terms back now. We'll get 3 altogether, and the sequence grows in this kind of pattern. The next one's going to be 5. The next one after that is going to be at 8, and so on down the line. Any questions at all, folks? Just thinking about how this recursive sequence works. Okay, Again, it's not too different from the other sequences we've seen. There's a lot of mathematics going on behind this. Turns into be a useful model for lots of things that occur in nature, mathematics as well. And there's a great formula for the nth term, which pretty strangely involves square roots and all sorts of irrational things. But here we're imagining we're not trying to develop a formula for the nth term. We just want to implement this as an algorithm, something that we could implement and run to get any term whatsoever. So that's what we're going to do in part A, just warming up, coming back from the break. We're going to look into writing the pseudocode. We'll do this both in homework and exam, which will return the nth term of this Fibonacci sequence. And for credit, we're going to be doing recursion on this one, mainly so that when we go to give the proof, this is going to be a proof on induction. And if we do this with the for loop, well, it's going to mess up this part right here down below. There's no induction proof for the for loop, in other words. So by using recursion, we can start by naming the function that we want to implement. It's a Fibonacci sequence, so you could say the whole thing, Fibonacci sequence, maybe with an underscore or a slash. But usually what I would do is just abbreviate this. I'm going to call it just briefly fib for Fibonacci. We're going to define a function. And as far as pseudocode writing goes, there's no hard and fast rules on how you format this. Sometimes people format this more along the lines of if you've done a lot of coding in C++, it might have a flair to that, and that would be absolutely fine in this course. If you've done a lot more coding in maybe Python, the way you format your pseudocode might be reflective of that, and again, that's completely fine. The way I'm formatting my code is a little bit more reminiscent on how you would actually run it in RStudio. Once again, only because this is just a fast platform to show a classroom demonstration. You're not required to work with this whatsoever. We're going to mostly focus on the pseudocode for homework credit and exam credit. But we'll be pulling this up and running things just to give a demonstration on how things are performing. So here's the function that's going to take the argument n, and it's going to output the nth term of the Fibonacci sequence. There's really three different cases. Either n was 0, or it was 1, or the input n that you gave the function was greater than or equal to 2. So we can write a three-case if statement, an if, an else if, and just an else. So it would look like this. If n, here we put double equal to 0 to make a comparison. If n is exactly equal to 0, then we should be returning just the 0th term of the Fibonacci sequence, which is 0. So all we say here is return 0. So that implements that first term. Next, if we pass the function 1, we have to return a 1. So we can say if n is exactly 1, return 1. And so far in this pseudocode, there's no recursion whatsoever that's occurred. This is just a case-by-case function. And I think I should format that a little bit better. What I wanted here was else if. I'm not going to be super picky on the pseudocode, you're right, but that's going to cause a problem if I try to execute this. Let me go else if n is identically 1. So sorry for the quick revision right here on the else if. So we have those two cases down. So now we need a case for when n is 2, 3, 5, and so on. We don't want to implement all of these things because that's an infinite amount of work. So instead, we use the recursive definition from here. We can say here, just a simple else now. This is the remaining case. We don't have to say anything here, so we're going to pass an integer. Notice this is basic pseudocode. There's no error checking whatsoever. So if someone passes a -5 or a 1.2, odd behavior could occur here. But if we're thinking we know it's a Fibonacci sequence and we're putting in appropriate inputs, the else is going to be the last possible case. We'll return. And this is always kind of interesting a thought for me every time I write this. We're going to return this essentially, which means we need to call the function that we're writing, Fibonacci itself. fib is how we implemented it. So we need to return the Fibonacci algorithm at n-1 to start. Add to it, we're making two function calls at once. Call Fibonacci again at n-2. So that's going to be the close bracket for else right there. Got mixed up on my delimiters. Close a parentheses for the definition of the function. And this is just one way to see the Fibonacci sequence. And as a pseudocode algorithm, this is just another equivalent way. Any questions with that implementation so far? Okay, now that we've got it in, if you have anything pulled up where you can write some fast code, this is a good way to test if it seems to be working as appropriate. So we couldn't do this on an exam, but this would be something you could do for homework. Although it's not required, it's sometimes kind of fun just to test things out, see if this is really going to work as intended, especially if your function has recursive function calls like this. So let's implement this. We're going to call it Fibonacci again. There'll be a function with input n, and we have three different cases we'll implement. If n is 0, return 0. So we've implemented that part. Else if n is 1, return 1. So we've got that part in. But of course, the really weird part of this whole pseudocode down below is that line. So we're trying to implement this part, and we're going to say else, return Fibonacci. So call the function that we're writing at n-1, add to it Fibonacci at n-2. So my claim is this should work, so let's test it out. I didn't get any errors down below, so that's encouraging. Here's a couple quick tests that we can run. We can see if it's actually executing the initial cases. So if we call Fibonacci at 0, we better get a 0. That's encouraging. We're on the right track. We should get a 1 if we call it at 1. So that's encouraging still. We carefully worked out these cases. So if we call it at 4, Fibonacci at 4, we had better get a 3 like we worked out by hand. And hey, it works. We get 3. And now we can do some crazy function calls. What about Fibonacci at, say, 40,000? Stack Overflow. It was not happy with that. Invoking abort restart during wrap up. I think I just put in too many terms there. Let me see if I can pare that down. 400. Well, it's working hard. This is not the world's most efficient code, right? If I put in 400, it's got to do loads and loads of recursive function calls. So this is a little stop button to abort the execution. I should have known that 40,000 is just not going to work for a computer like this one. This is an all-in-one machine, by the way, if you're wondering, over Zoom. Wondering how long we want to give this. Good news is there's a formula for the nth term, so that might be a faster by hand computation. Let's maybe abort this one. Sorry for the misadventure on this. How about 40? Let's keep this a little bit more down to size. If we do it at 40, that should run. Let's hope for the best on this. I should have practiced this out on this computer before trying it out for a classroom demonstration. At 40, we're still making loads and loads of recursive function calls. This core computer, I can hear the fan spinning up on it. Wildly inefficient code is what we're looking at so far. How about we let this run for a bit and then see if we can prove that this actually runs. Our test here is probably giving us a little bit of doubt that this is going to run as intended. by trying to make this happen on a 40 for Fibonacci. You'd have thought it would be a little bit faster. So let's see if we can come back to that and see what it outputs. For the moment, I'm still feeling somewhat confident that this code should run as intended. It definitely ran on some of the lower values, less recursion there. So now we're going to see if we can use strong induction to prove that it really does return the nth term, just really, really slowly. It's still working on this one. So let's write down first what we're about to prove. We have a predicate that we're going to define. P at n is going to be the statement that this, again, wildly inefficient code, this Fibonacci pseudocode at the nth term will return the actual Fibonacci sequence, Fn. So this is the predicate function. The statement we want to prove is that for all integers n, this statement will come out as true. And in this case, it's going to start out at 0, so we'll quantify that as well. Oh, good question, Sophia. So f at 4, what I did for this one was, using that index 4, I had to plug in the value for n minus 1. So that would give it a 3 altogether. So that's where the 2 comes from. Now it might be cleaner to just write this in as f at, excuse me, that should have been an f at 3 altogether. So for the 4, plug the 4 here, and that's where we'll get f at 3. Then plug the index 4 here on that subscript, we'll get plus f at 2. And that's where we got the 2 plus the 1, giving us a 3. And Sophia says, but how did you get the 1 plus 1 at f at 3? So for this one here, same kind of idea. Let me see if I can include just a little bit of space. For the f at 3, let me double check my work as well. If I put in a 3 here, this one would turn into f at 2. Then 3 here would give us at f at 1. And then checking f at 2, we have a 1 value there. So that's where this one came from. And then f of 1 is how the sequence started. We plug this one here, down here, and that's what gave us the 2. Yeah, you bet. Thanks for asking about that. And the fan has stopped spinning, so we got it. Here's Fibonacci 40. We can see how doing Fibonacci at 40,000 was a misadventure, how we got a stack overflow. The number is just too gigantic. At 40, here's the number we get. It's probably, in most cases, a little bit higher than that. It's going to start using scientific notation to describe the size. Doesn't grow as fast as factorial, but this definitely does start growing quite rapidly. Well, we've got a number for Fibonacci at 40, but now we're wondering, is that even correct? Who knows? We're going to prove it by showing this pseudocode here runs as intended. So we have a predicate function P of n, and we'll prove that for all n in Z greater than or equal to 0, P of n is true, that this is really going to return the nth term of the Fibonacci sequence. You just might need a more powerful computer if you're trying to execute it at, say, very large integers like this. Other questions at the moment before we get started? George says, according to O complexity, the recursive version is approximately 3 million times more complex than the for loop. So that's an impressive analysis. Thanks for mentioning that, George. And that's good reason why this is struggling to just do Fibonacci at 40. So for loop is a much more efficient implementation, looks like, based on the O complexity. And once again, we could also do something along these lines. This is not very effective code either. This is pretty rough to get the end term of this sequence above. Same kind of idea, just like the Fibonacci sequence, slightly more complicated, but really the same kind of thing. If you can find a formula, that's what we were really proving in the prior problem. This is going to be the most efficient at all, right? So if you really need to work with the Fibonacci sequence, probably avoid recursion, avoid even the for loop, and develop the formula for the nth term. There really is one out there. Kind of an ugly looking formula, but it does the job. But thanks again for mentioning that, George. That's pretty interesting to see just how radically inefficient this really is. Other questions or comments at the moment? Okay, although it's the most inefficient pseudocode we've written down probably so far in the course, not too different than this really, we can still prove that it's going to run as intended. So here, we're now looking into the review of the strong induction technique. Strong induction requires that we prove the base cases. Here, just like the other problems in the notes, we really just need to prove two. It's going to line up with the if and else if in our pseudocode. Then in the inductive case, we can make a general assumption that all prior cases up to an n-1 are true, and that will imply the nth case is true. Really, we're going to investigate the else case and show that this is going to run as intended by proving the inductive case here. George says, I forgot to mention, that only applies for the value of n is 40. Oh, I got you. So complexity is dependent on the n value itself. Thanks for mentioning that. So that would tell us complexity for this one is going to be just pretty insane compared to the for loop. Probably the separation is going to grow at each additional value that you throw in there. Well, let's give this a try. As far as the base cases go, we're looking into these two parts here and here. So we start by assuming, if we're going to prove this, let n equal, on all the prior examples, we were saying let n equal 1, but here, if we start at a minimum value of 0 to kick off the sequence, much like how we have 0 here and 0 here, we have to start at that value as well. So let n be 0, and we need to check two sides. We need to check the pseudocode and the sequence to make sure everything is going to run as intended. So let's see what happens first with the pseudocode if n is 0. If n is 0 and we run this function, we are going to execute this block. So we can say here, then the if block executes and returns one and only one thing, that's 0. So that's us looking at what Fibonacci at n is going to return. I wrote fin there. That should have been a FIB. Sorry for that distraction. Just noticed it. So we return 0 when we run this at n is 0. We check the sequence as well. The sequence starts with its initial value right at 0. So we can now say, since f at 0 equals 0 as well, p at 0 will evaluate to true. So that's one base case down. We're going to check the second base case on the else if, and that's going to take us through part 1 of the strong induction technique. So same kind of song and dance. We just increment the integer by 1. Let n equal 1. Now we trace our code. If n is 1 and we run this, passing the input 1, we skip this block, and we're going to run the else if block. So we can say down below in our argument, then the else if block executes and returns one and only value, just 1. It feels like we're saying just about the same thing. We're just focusing on a different term. We have to check that we're really getting the Fibonacci sequence correct term, and it is at 1. F of 1 gives us the same exact term 1. So we can say here once again, since, let me see if I can scroll just a touch here. Since f at 1 equals 1 as well, p at 1 comes out to true. So we have true on both of these base cases. We've double checked. The left-hand side, whatever it's returning, is the same as the right-hand side, giving us the correct nth term of the Fibonacci sequence. Now we are essentially just double checking that we have those terms. We need to show it works for all terms n greater than or equal to 2. So that's where we jump into the inductive case. Any questions first before we go to that next phase? Okay, let's take a look at that. Let me see if I can screenshot this real quickly for us. So this is the pseudocode that we're trying to show runs as intended. Very, very inefficiently, but it'll get there if your computer is powerful enough. We have the base case down, and I'm just trying to get everything on the same screen here. Okay, that should do the job for us. Base cases are down, and now for the inductive case, here's the next assumption we're going to make. Let's assume, let's begin maybe with the index, let n be greater than or equal to, and now the major idea here is, because we're tracing this execution, we need to be very particular about that index. But another thing to think about is, if this was your last base case, whether that was a 5, 7, or 12, you go one higher. So if that's a 1, in the inductive case, we're going to let n be 1 higher, greater than or potentially equal to 2. And the other thing that we mentioned with these kind of proofs is it should match up with this part right here when we're defining the nth term recursively. So this part needs to match up with this part right here. So if n is greater than or equal to 2, we're going to make one major assumption. Assume that p at n minus 2 and p at n minus 1 is in fact true. Let's track that through strong induction. We could also assume p at 0 is true, p at 1 is true, all the way down to these last two cases. The reason I only used these two assumptions is because the recursion is based off of these two parts right here in the pseudocode. That means you can assume all prior cases are true as well, but we're only going to use these two portions here and here. So once we make that assumption, we're saying that if we put in the right index in P of n, we're going to return the right nth term, but only for these two values here. So I'll say immediately what this means. This means from this part right here, once we assume that this is true, we plug Pn minus 2 into this predicate function, and we have the statement that Fibonacci at n minus 2 returns the n minus 2 term of that true sequence. Then same idea for this one. Let's connect it with an and. Fib for the Fibonacci sequence at the n minus 1 value, that's plugging n minus 1 back up here, will return the n minus 1 term of the Fibonacci sequence. So I'll just say briefly, returns f at n minus 1. So those are the two connections that come from the inductive hypothesis right here. We're trying to prove a true implication that assuming these two come out as true will then imply in our direct proof that P of n will be true. And will P of n be? That the nth term, just leaving n as it is here, will return Fibonacci nth term of the sequence. So if we can get to that statement, our work is entirely done. So, well, let's work the same way we did the base cases. When we showed the base cases held at n is 0, n is 1, we looked at the left-hand side, that's our pseudocode, showed what it returned. Then we checked on the right-hand side and showed we had the correct nth term of the sequence. We're doing the same exact thing in the inductive case, but now we're making substitutions to make this happen. So I'm going to start at the left-hand side, tracing the pseudocode. That's where this became critical as a statement. If n is greater than or equal to 2, we skip the first if block. We skip the else if block. Only this block is going to run at this point. So let's save that down on paper. Since n is greater than or equal to 2, the else block runs and returns this whole sequence, or excuse me, not sequence, but this whole expression down here. So it returns fib at n minus 1 plus fib at n minus 2. So these are two new function calls that have to run at this point. But we also made this strong assumption here that fib at n minus 2 will return the Fibonacci sequence at n minus 2, and fib at n minus 1 returns the correct n minus 1 term of the Fibonacci sequence. So now we can make two substitutions here. And you could write equality right here if you'd like, but because these are true function calls, I think it's a little bit more standard to say returns what this pseudocode is actually going to return. So I'll write returns. Now we're putting in these assumptions, fn minus 2. Hang on, let me go in order. So fn minus 1 at fib for Fibonacci returns the correct n minus 1 term of the Fibonacci sequence. Then add from over here, Fibonacci at n minus 2 returns the correct n minus 2 term of the Fibonacci sequence. Once we have those two down on paper, here's where we need to cite the definition of the Fibonacci sequence. Let's see how far we have to scroll. All the way to the top. Let's just screenshot this down as well. Okay, for this quick citation here, when we see fn minus 1, that's this term, plus fn minus 2, that's that second term. And so now this is just a mathematical expression. Equality is pretty standard at this step. We can say that this is truly equal to f at n, because that definition here held for n greater than or equal to 2, which is appropriate to that assumption at the very beginning. So what this has now shown is, through that quick check on the definition, when we go to run a value n greater than or equal to 2 inside Fibonacci, it does these recursive function calls, but it in fact returns f of n. So let's say that all together. This means fib at n returns nth term of the Fibonacci sequence. So what we've shown all together is this assumption way over here, p at n minus 2 and p at n minus 1, in fact, directly implies that p at n is also true. So we can say this is proven. And this concludes the induction proof right at that step. So again, maybe not the world's best code for implementing this kind of recursion. But as far as proving it goes, we showed that if we assume these two cases here, and we have the base cases nailed down, running as correct, then assuming two prior cases as true, will prove the next term is also true as well. So at this stage, through induction, we have now shown for all possible integers n greater than or equal to 0, this pseudocode below runs as intended. It really will return the nth term of the Fibonacci sequence. Well, we did it, folks. This is really working with the Fibonacci sequence, but the main takeaway is just practicing writing down pseudocode a little bit further, working with it, proving that it runs as intended is, in a certain sense, a kind of trace showing exactly what would happen at various values of the integer n. But any last questions or comments, folks, on this last induction proof? Okay, again, we've looked into a good amount of pseudocode so far, but one thing we've mentioned is a lot of the stuff that we've been doing in chapter 5, was to try to get prepared for what's going on finally now in chapter 7, where we're at. Chapter 7, we're going to look into lots of various algorithms. Our author has pseudocode that's already written out. He proves in the reading that the pseudocode implements, say, the Euclidean algorithm or the division algorithm correctly. And if you like, reading that proof is very informative. But if you decide to skim through that, no harm done. You would not be thought of lesser if you decide to skim through some of those proofs. They do get very involved. Really, he's not doing anything too different from what we've done here at its heart in many of those proofs. Induction comes up, so it's a pretty good challenge to trace through his arguments. But the main takeaway that what we're going to work on in chapter 7 is understanding how to trace these algorithms through the procedures that's already provided in pseudocode. So that's one of the major objectives of the course, working with pseudocode, either writing it like in chapter 5, or understanding it and tracing it like we're going to do in chapter 7. I do have a revision here, but nothing major and any corrections. I just change around a couple numbers to make the exercises a little bit more interesting and not too tedious. So here are some of the major algorithms we're going to look into. We have the division theorem, sometimes called the division algorithm, we're going to look into. This is really going to just be another look into modular arithmetic, so that'll be kind of exciting. But that particular division theorem or division algorithm gives us this as a pseudocode. So we're going to look at how to implement modulus as well as a divisor at the same time through this code. Really compact and concrete on that running. Then the next objective we'll take a look into is, I changed a couple numbers I wanted a false on here, and they were all 3 true, so I made this one 14 to force a false to make the exercise more interesting. We'll look into properties of modular arithmetic. And then this is going to be the major code that we're going to take a look into, the Euclidean algorithm. It's going to give us a greatest common divisor for a couple integers that we provide. It's really compact pseudocode altogether, so we'll show how to trace this one as well. Some of these problems get a little bit more challenging because occasionally we're going to look into some algorithms that are recursive, just like we saw in the prior chapter 5. So in section 7.3, primality, relative primality, this just grows a little bit more and more, but we'll be practicing these carefully as we go. But first, we're going to start at the top. If we're talking about modular arithmetic, we have to have a good notion of divisibility. We'll lead into the division algorithm, or the division theorem, as our author calls it, and start working with properties of divisibility below. Well, this will kickstart our number 3 chapter. Any questions first before we begin? Okay, first bit we have to get through is some deceptively tricky notation. So if we pick 2 integers, one that's non-negative, k greater than 0, and some other integer n could be 0, positive, or negative, we write k bar n to mean n mod k is 0. Notice the switching around with this notation right here. When you see k bar n, I'd say a really good strategy here is to always mentally read out in your mind what you're really saying is k divides n. And it's a distraction because you definitely don't want to think of it like this. That's the wrong thought. We're not saying n's dividing into k. It's sort of backwards how we sometimes write fractions. So k bar n is going to be the statement k divides n, meaning it divides it evenly. In other words, n mod k is 0. So this is our notion of k dividing n evenly. The modulus is 0. There's no remainder altogether. So we can also say if k bar n, if k divides n, then n is a multiple of k, and k is a factor of n. So 3 different kind of notations or concepts all wrapped into each other. Modulus, multiples, and factors all come from that statement, k bar n, or k divides n. So just for the sake of practicing with that notation, I have a couple fast examples down below. Example one just asks the short question, which propositions among the two below are true? Probably not a real exam question, but just a good one to tie together definition 7.6. So if we start off with this one, it's saying, read this out as 21 divides 3. So this means 21, oh, got that backwards. 21 divides 3. In other words, the modulus is 0, or the division is even, but you could also say that in a different way. If 21 divides 3, then the result would be inside the set of integers, z. But that's absolutely not true, right? This is not a whole number whatsoever. The remainder after division is 3. So if we do this modulus right here, we would be doing 3 mod 21, which is 3. It's not 0. So this is false. So that's just, again, quick tour of what the notation is saying. 21 divides 3 is absolutely false. The modulus is non-zero on this. It has a remainder 3. If we change the notation around, 3 divides 21, this would mean 3 dividing into 21 is in z. It's an integer. That's absolutely true. That's 7. Oh, the words, you could also say this means that 21 mod 3 is 0. That's absolutely true. When we divide 3 into 21, we get remainder 0 altogether. So either way you decide to look at it, from the modulus equation or whether it's a set of the integers, this is true. Well, that's our definition so far. Any questions at all, folks, with the way the definition is worded or otherwise? Okay, right out of the
Sorry,
gate.
my microphone was being futzy. Um, isn't it? I'm just wondering, for the second half of the definition, n divides k, and then n is a multiple of k, or so n is a multiple of k, and that k is a factor of n, isn't that an identical statement?
Yeah, pretty much. Absolutely. These are really saying the kind of same sort of thing. When we're saying n is a multiple or k is a factor of n, it's absolutely pretty much the same thing, just said in a different way. And let's maybe write something down to go along with that. So if we say k divides n, this is really just saying, oh, got that backwards again. This just means k dividing into n is in the set z. But then what would that mean? That just means that there exists some, I can't use k. Well, I shouldn't. It's already been used. I don't want to use a subscript. Let me use a different value. Let's say, how about a? There exists an integer a in z such that if k divides n, that means when we divide it, we get that integer a. And then we get the multiple statement if we say from this equation here, if we say multiply by k, including the denominator, it would mean n equals a times k. And this is where this statement is coming from. N is a multiple of k because it's the eighth multiple, in other words, 8 times k. But then just like you said, k is a factor of n, same exact statement, just a different take, a different way to think about it. K is a factor of n because here's the factorization. N is 8 times k. So yeah, absolutely. These are really just synonymous ways to look into the overall concept, k divides n, which means all of this is the same as the concept n mod k is 0 in a certain sense. Lots of different ways to think about that one modulus function. N mod k being 0 means all of this stuff is true. But any questions about that so far?
Just kind of, how deep is this class going into like fundamental theory of mathematics?
I would say we're getting into equivalence classes, which is pretty far into fundamental theory of mathematics, depending on the meaning of that so far. So equivalence classes are going to take issues of, say, this equation right here, issues of transitivity. Or hang on, transitivity would be this one. Transitivity. It's going to take equations like this one. This is really an equation of reflexiveness. Let me spell that correctly. Reflexive. Oh dear, Control Z is failing me. Give me a moment. We're going to look into things that are transitive, reflexive, symmetric, look into concepts called equivalence classes, which is a way to extend ideas of just ordinary equality of integers into larger cases. If you've taken anything along the lines of, say, linear algebra and done row reductions on matrices, row reduction is a relation that provides equivalence classes, which has reflexive, transitivity, and one other property that's missing from this list, symmetry. So aside from the logic, the proofs of proof techniques, that's going to be our major area where we're going to go into for foundations of mathematics, looking into equivalence classes. Does that make sense with that question there?
Yes, thank you.
You bet. Other questions or comments so far? Okay, so we have an interesting definition. And let me put one more statement here to just kind of tie together this entire line of thought. This all came from just writing down on paper once. K divides n implies you have an element in Z when K divides into n, which implies we can quantify by putting in that particular element. You could rearrange the equation, and at the same time, this also means n mod K is 0. So lots of concepts all being unified together. If we wrap this together with properties of divisibility, we have pretty standard properties that we've seen before. We just have to think about what the notation is saying altogether to really make sure what this is saying. For example, if you're thinking about issues of division by 0, this one's not an issue because this is saying A divides 0. We should be a little bit careful with that though, right? This is for A not 0 in the very first place. 0 divided by 0 is also undefined. But if A is non-zero, A absolutely would divide 0. It would be 0 itself. This is saying 1 divides A. We know that to be a mathematical fact, whether A is an integer or not. But now we have some other interesting and unusual properties, like, say, transitivity. If A divides B, and if there's an intermediate division, if B divides C, well, because A divides B as well, A has to divide C as well. This is going to be an interesting fundamental property. Essentially, it's a property of equality that we use and abuse all the time. When we write down a long chain of equalities, we can say the left end is completely equal to the right end. We're using transitivity. But a lot of algebraic mathematical structures have transitivity. Turns out divisibility is just one more on that list. Then a couple more properties just for the sake of completeness. If A divides B and B divides A, that's unusual, right? If this always works for any element A and B, this would be a symmetric relationship, but that's not true. 5 divides 15, but 15 does not divide 5. So if these are both true, that would mean either A and B are identical or they're opposite of each other. And finally, this is kind of a distributive property in a certain sense. If A divides B, A divides C, and you sum B and C together, A has to divide the sum altogether. So we're going to prove one on the list. I think transitivity is kind of the exciting one, so we're going to go for that. You'll be doing one as well in the homework. Any questions at all, folks, before we give this proof a try? Okay, so here's the statement. We're proving transitivity altogether, but really the major thing we want to be careful with is the notation at the same time. The proof can be attacked at in a lot of different kinds of ways. For example, if you so chose, you could focus on the modulus aspect when thinking about divisibility. If you would like, you could think about quantifying things in these terms. You could rewrite them, focusing on multiple or factor statements as well. So there's lots of different ways you could prove transitivity. Here's one way that I would probably think flows the easiest. I want to focus on writing down the fraction. I think that can flow pretty nicely when working through this one. So let's say here, we're going to prove if B divides A and C divides B, then C divides A, but let's rewrite this statement just to get a different view of it. B divides A, C divides B, then C divides A. So let's write down both of these statements all together. Notice that it's an if-then statement, so we can also rephrase this as B divides A and C divides B implies C divides A. And just for emphasis, we could put a bracket here to say this conjunction here implies that as a conclusion. C must divide into A altogether. So let's give the proof now. We're not doing anything too fancy. This one's a direct proof. We're proving just the same kind of problems we did in section 3.2 with the implication. We start by assuming this part is true. If we make the assumption that this is true, much like with the induction proofs as well, and we can conclude here that C must then divide A, our work is done. So let's start by saying, assume B divides A and C divides B. Next thing we should do is just say immediately what this would mean. And again, you have a lot of options for expressing this. I want to start off as writing this as a fraction, saying that we have an actual fraction we can put down on paper, but maybe actually focus on the multiple definition. Let's see how this goes and make a decision. We can say this means we're unpacking the definition of divisibility. Starting with this one, B divides A, implies there exists an integer k in Z such that when we take A divided by B, we get k altogether. So that's one way to write divisibility. For this portion right here, same idea, just different letters. If we have C divides B, then this would imply, and let me use subscripts here. I forgot there's two values. So let's start with the K1 and go K1 here. And next go exists K2, or a different letter if you prefer not using subscripts. Exists K2 in Z such that we said C divides B, so B over C equals K2. So now we have two fractions, but on both of these, we can rewrite them. Then A is going to be equal to B times K1, and C is going to be equal to, or rather, let me try again. That's some bad algebra there. Multiplying this one by C, B is going to be equal to C times K2. So from these two fraction equations, we can rewrite them in this format right here. And what we're trying to show is C divides A. So far, I haven't done much except for wrote down what assuming the hypothesis here would mean on paper. It lands on this stage right here. We have two equations here. B is a factor of A, C is a factor of B. Any questions to this step so far? Okay, at this stage, we're basically done. These kind of proofs aren't too bad because really all you have to do is follow your nose on what this says. If B divides A, go to the definition, write down in whichever format you'd like to focus on, and then just run the proof through. So that's what we did to start it out. And now to land on a conclusion, C divides A, we could just write that out. Put down C dividing into A. Let's see if this works out. If C divides into A, we can make a substitution here. A is equal to B times K1. So there's one substitution in for A, but we have another equation for B, so we can make yet another substitution. This means in place of B, we can put C times K2 times K1. And ordinary operations on arithmetic would say, well, C's cancel. We get K1 times K2. Then we use closure of the set of integers under multiplication. K1 and K2 were integers to begin with. Multiplying integers gives you an integer, so we can say this is an element of Z. But that tells us, well, that's just the format of what we mean by C divides A. We did the division, we have an integer result, and so now this tells us that C does in fact divide A. All I've done here on that last statement is just switch to the new notation that we're focusing on in the division properties. So the proof that you're going to take a look into on the homework goes pretty much about like this. And really it's up to you how you'd like to write it. Some people might focus on the modular aspect. Some people might focus on the fraction, or if this makes more sense in the problem, you can write them out as multiples. But any questions at all getting through this one? Okay, well, the major goal that we're getting through here in this section 7.2 is getting into the Euclidean algorithm. But to get there, we have to make a couple stops. The next stop is looking even closer into the modulus function as we worked with it all the way back at the start of the course in chapter 2. And the way we're going to take a closer look into the modulus function is through the so-called division theorem. And again, you might have heard of this, read about it in other places where it's often called the division algorithm. The division algorithm makes some pretty powerful statements. Some of the most powerful parts of the division algorithm are the uniqueness itself is what makes this an incredible tool for the algorithms that we're going to develop. But let's start from the beginning. Also note it's a floors and remainders theorem is another way to call this, or the divisions theorem. So these two things enter into the problem. But when you hear remainders, think modulus. So the floor function, the modulus function from all the way back in chapter 2 makes a comeback here. It says start with a value k that's an integer greater than or equal to 1 and is an arbitrary integer, either positive or negative. If you have any two integers that follows this format, only requirement k is greater than or equal to 1, there's an existence part. There will exist an integer d and r satisfying two equations. R might make you think of remainder. That's what it is in this problem. The remainder is either 0, that's if the division is even, or it's strictly less than k, the thing we're dividing into. R is essentially the modulus in this problem. Well, there exists two integers, r and d. D is the divisor, which gets mixed up into the floor function altogether. And here's where the divisor is working in. Equation number 2 is that k times d plus r equals n. And once again, the major powerful part of this division theorem is that d and r are unique. The divisor and remainder that we come up with can only solve these two equations in one and only one way. Well, that's the whole statement of the theorem, but if you're like me and you look at this theorem and you say, hang on, it's called the division theorem or the division algorithm, and there is no division here, you're not alone. That looks kind of funny in a way. So if it just helps to visualize this, here's another take on it. When you see this equation right here, it could just be reformatted in the sense that what you're really doing is dividing n by k. That's where the division portion really comes from. So if you rewrite this as n divided by k, you're allowed to do k is greater than or equal to 1, so no divisions by 0. What you would get is the divisor plus the remainder is still divided by k. Excuse me, I said that weird. K is the divisor, d is the quotient, n is the dividend. There's all sorts of new interesting words when it comes into this format here. And r is the remainder, still being divided by the divisor k. So this is an equivalent way to think about it, but the standard way to actually write it down is in this part right here. So that's the division theorem. Essentially, it's going to work with the modulus function to produce both of these values, d and r, to solve the equations. Well, any questions at all, folks, with the division algorithm so far? Okay, my next two examples, really their whole purpose is really just understand what the division algorithm is saying by working out values in part B. But the heart of the division algorithm is really modulus. So we're going to start with the part A, then use the theorem directly for a specific k and a specific n coming from this division algorithm. So another refresher is that if we talk about the modulus function and write down n mod k, there's a lots of ways to work with this. And one nice formula that we've taken advantage of is that this is equal to n minus k times the floor of n divided by k. So even though this one's kind of fast to work with, let's work it through this definition here just to see how all this information here combines. So if we take 248 to mod 15, some of you might already have the answer, but let me work it out through first principles. 248 mod 15 means take 248 minus 15 times the floor of 248 fifteenths. This is a floors and remainders theorem, so there's some value in actually working this out. There's where the floor is in the division algorithm. I want a quick calculator to help us out here. Forgot to load one up. Give me a moment. So 248 fifteenths is that integer here. I'll just write down 16.5 altogether. So this is equal to 248 minus 15 times the floor of 16.5. The floor of 16.5 is exactly 16. So this is 248 minus 15 times 16. And that's the floor. That's the value d coming from the division theorem. So even though this equation wasn't necessary, actually working it out gave us half the answer when we go into part B, finding both the value r and d at the same time. Then on the next step, let's work this out further in the calculator. We take 248 minus 15 times 16, we get 8. That's just our remainder altogether. So 248 mod 15 is just the remainder after dividing 248 by 15. That remainder is 8, but that's just the integer r in the division theorem above. I'll try to say division theorem since that's what's printed out in the textbook. Often I'll forget and call it the division algorithm. It's kind of just a reflex when I say it that way. So now returning to k is 15, n is 248. Think of this as the n, that as the k in the problem, same as this k and this n. We can now solve equation 2. But first observe the value r, the remainder that we provided, has to be either 0 if the division is even, if say 15 does divide 248, or has to be strictly less than k. So when we got to remainder 8, it's comforting to know that yes, that is strictly less than 15. So the inequality in part 1 is automatically satisfied. Part B just says, find the integers r and d satisfying theorem 7.1. really we're just focusing on part two fundamentally. So in part two, we have KD plus R equals N. Throw in our value for the floor, which is the divisor, R, which is the remainder. Use our values for K and N that's provided, and we can now say that 15 times the divisor, which is 16, plus the remainder, which is 8, equals 248 in the division theorem. In other words, what we've expressed is D must be equal to 16 and R must be equal to 8. So every single time we've worked this formula directly, we didn't make a big deal out of it at the time in chapter 2, but we really were just using the division theorem altogether. You know, one thing you might want to do just to double check everything is working as intended is verify that equation there really works. Take 15 times 16 plus 8, observe it's really 248, and hey, it works. The big part of the division theorem is also saying those values for D, the divisor, or you could call it the floor, and R, the remainder, or you could call it, really it's just the modulus, are unique. There's no other values that you can come up with satisfying both the inequality and the equation. Well, that's the division algorithm, just extending a little bit about what we know with modulus so far. Any questions or comments at the moment? Okay, there's one more problem we'll take a look into just for the sake of completeness. When it says let n be an integer, it means positive, negative, or zero. The division algorithm will still apply. And so that's this throwback problem here. We've actually done this one before. I think this one might have been a homework problem, but I felt like it'd be a nice idea to come back to this one to see how it works. Because working modulus, when you have a negative value for n, always just looks a little bit weird. The reason we get a value from this, and the reason the value is what it is supposed to be, is really the division theorem. When we took a look at this kind of problem before, we wrote a number line, and we try to argue on the number line, it's the smallest distance between one multiple and the next. And I think a lot of people don't really care for that justification of what this comes out as and why it should be what it is. But the division theorem makes this extremely concrete. If you do negative 42 mod 17, you will come up with a D and an R, and those are going to be the only two unique values satisfying these two equations. So this extends our understanding of modulus even further in the case of negative values. So this is our n value, this is our k value. We'll work this equation directly because again, it gives us the floor, the divisor D. So take negative 42 mod 17. That's going to be negative 42 minus 17 times the floor of negative 42 17ths. So we've got a floor exhibited. This becomes negative 42 minus 17 times the floor of, now we need a calculator, negative 42 17ths comes out as a negative 2.4. Rounding doesn't have to be too specific. I'm just going to round this with truncation. You'll get the same exact value of the floor either way. So with the negative 2.4 here, when we go to take the floor of this one, be careful, think about this thing in terms of a number line. This one will come out as a negative 3 altogether. So this is negative 42 minus 17 times negative 3. So now we have the value D in the division theorem. All we need to do is crank it out and get the remainder, the actual modulus R itself. And let's double check that this works out. K is 17 here. So if we are outside of this range with our remainder, we've got a big problem. So we'll check this out immediately at this stage. So negative 42 minus 17 times negative 3 gives us a value 9. And that fits. K is 17 in this problem. If we've got a negative value, that's very alarming, right? This is saying strictly non-negative and smaller than what your divisor is going to be, K. So now that we have 9, our work is essentially over. We just combine those two values in the next portion. Any questions at all, folks, running through part A? Okay, well, let's finalize this one. There's not too much more to say. We'll just write let R be equal to 9 and D be equal to -3. We have a negative value here for the quotient, D, portion right here, the floor, however we'd like to call it, only because of the input N was negative itself. If that's the case, then we take KD plus R. K is going to be 17 times -3 for the value D, plus the remainder 9. That had better come out as the N value, which is -42 from the very beginning. And again, if you decide to format it this way to do your checking, no harm done going that route. This is a faster verification because we don't have any fractions to worry about whatsoever. And 17 times -3 plus 9 is in fact -42. Really, all that we're looking at right here is just kind of a rearrangement of what we were dealing with over here in a certain sense. We get -42 altogether, verifying parts 2 of the division theorem. So our work is done. That's the so-called division theorem or division algorithm. All it's doing is combining two very useful functions, modulus for R and the floor here, which is going to be the quotient upon division. Well, any last questions, folks, on running through this theorem? Okay, again, the ultimate objective in section 7.2 is to get to the Euclidean algorithm, see what it does for us, working with Gray's common divisors. But to get there, this algorithm right here, mod and div, is a core component of the Euclidean algorithm. All it's doing is taking this, the division theorem, and implementing it as pseudocode. So it's called mod and div because we're getting two values altogether. If we take mod and div of nk, we run an output n mod k and a floor and divide by k and return the two values r and d that are the same values here, d and r, in the division theorem. So we'll take some time running through this when we come back on Thursday's class. We'll trace the execution of this. We'll implement it into R to see how it runs. Here's the implementation extended for negative values, so we can run a negative modulus as well and see how all this works. Then we'll push forward on Thursday, looking into other properties of modular arithmetic and put in that division, that mod and div algorithm inside the Euclidean algorithm here. But any last questions or comments, folks, before we call it a day? Okay, well, this stuff has been pretty interesting so far. A lot of the things that we're developing here, we're going to see as it comes back later on in our chapter 8, dealing with relations, symmetry, transitivity, reflexivity, and later on in equivalence classes like we mentioned before. So think of a lot of what we're doing is just extending into other additional topics with the goal of eventually introducing relations. But have a great afternoon, folks. We'll be back to this on Thursday.